Welcome to the Science for the Public lecture series. Science for the Public is an organization committed to bringing science information and issues to the general public. Visit our website for our program listings and blog.
Welcome to the Robbins Library. My name is Andrea Nicolai, and I'm the Assistant Director. And I'm thrilled to welcome you here this evening, on a beautiful spring evening, for this Science for the Public program. This is Yvonne Stapp, and she's going to be talking to you a little bit about Dr. Max Tegmark, who you all probably know a lot about anyway, but we're thrilled to have you here, Dr. Tegmark, and thank you very much for coming.
Thank you so much. Thank you, Andrea.
Yeah, good evening. I'm Yvonne Stapp for Science for the Public, and I welcome you to a special public science lecture at the Robbins Library. Tonight we have the honor of a presentation by the one and only Max Tegmark, that's for his fans, Professor of Physics and Cosmology at the Massachusetts Institute of Technology. Dr. Tegmark, always Max, after the first introduction, was raised in Sweden, and he received 2 bachelor's degrees at different universities there, one in physics and one in economics. He then moved to the University of California, Berkeley for his graduate work and received his PhD there in 1994. He was a research associate with the Max Planck Institute in Munich for physics, and then a Hubble Fellow and a member of the Institute for Advanced Study at Princeton University. He joined the faculty of University of Pennsylvania, but then was rather quickly lured away by the MIT Physics Department, where he has been since 2004. Dr. Tegmark has made major contributions to physics and cosmology, some of which he will discuss tonight, and he's received numerous awards. He's also a fellow of the American Physical Society. Max Tegmark is a favorite among cosmology buffs, and especially those interested in multiverse theories. As a speaker and author of articles in things like Scientific American, edge.org, if you are familiar with that, and other sources for the general public, and in his many appearances in documentaries, including Parallel Worlds, Parallel Lives, probably familiar to a number of you about Hugh Everett. He's excelled at translating for the general public some of the most challenging concepts in cosmology. He's developed a substantial fan club, as all of you know, in the process, because he's made these concepts so interesting that non-experts forget to be intimidated and they realize this stuff is fascinating and important. And now he's written his first popular science book, Our Mathematical Universe, a very readable account of his ideas, which he'll be talking to us about tonight. And now, please welcome, our great pleasure, Max Tegmark.
Thank you so much for that all too kind introduction. It's a great honor to be here. It's great honor to see so many of you here, despite the beautiful spring weather that you could have been out in. And it's a particular honor to see so many of you kids here. This is absolutely awesome. And I am here tonight because I want to encourage you all to think big. Because we humans have repeatedly underestimated 2 things. Both the size of our world, which we've again and again and again come to realize that everything we thought existed was just a small part of a much grander structure, a planet, a solar system, a galaxy, a universe, and maybe even a hierarchy of parallel universes. And I'm going to ask my dear wife here to see if you can find any universe in here and blow it up for us. And but we have, in addition to underestimating the size of things, also repeatedly underestimated the power of our human minds to understand it. And I want to come back to that very optimistic theme as well. But first, let's remind ourselves of what we humans have managed to figure out so far about our place in space during the first 13.8 billion years of our cosmic history. So let's begin here on Earth. We begin in the Himalayas and just go for a ride. This is a very beautiful animation put together by the American Museum of Natural History in New York, which I love because It's actually exactly to scale everything, not just a bunch of fluffy eye candy. So when our distant ancestors, in fact Eratosthenes in ancient Greece, first figured out the full size of the planet we're on, people were blown away by how huge it was. Yet, of course, we now know that there are vastly larger things out there. Soon coming into view, you're going to see the orbits of the many satellites that we've managed to put up into the sky. And in the beginning, we didn't have rocket power. And as I talked about in the beginning of the book, it turned out we didn't need the rocket power to figure out great things about our place in space. We just needed mental power to let our minds fly. So here we have a lot of these artificial satellites. Soon we're going to start to see our moon's orbit coming into view. And we're not going to see the moon, though, because this is the scale. Okay, so the moon's orbit is so big that on this scale, the moon is too puny to even notice. The sun that you can see here in the background, just to remind ourselves of scales, it's so far away, it takes about 8 minutes for light to reach us from it, right? And most of the stars we see farther out here are so far away that it takes hundreds of years for light to reach us. So if you see some stars tonight, later on here in Arlington, and someone out there were to be looking at us, they wouldn't see us. But they might see, for example, the Boston Tea Party. That's how far away this is. So our solar system is vastly smaller than the stars, the distances to the nearby stars. And I'd like you to raise your hand if you know anybody who was born before 1925. My grandma was. Yeah. So when my grandma grew up, right, she grew up in a much smaller universe than the one we're talking about now, because to them, that was before they knew that there were other galaxies. That was only established in 1925 by Edwin Hubble, that this haze in the sky that we now call the Milky Way wasn't just some gas out there between the stars, that it was what we now call a galaxy with hundreds of billions of stars stretching which is so big it takes 100,000 years for light to go from side to side. And yet that galaxy is just a small part of a group of galaxies and clusters of galaxies, which in turn form these amazing filamentary patterns. This is from the Sloan Digital Sky Survey, the largest three-dimensional map of our cosmos so far made that I've had the pleasure of working with. So you see, even our galaxy is part of a much, much grander structure. And even these huge galaxy clusters themselves are part of something even bigger, which is only now gradually coming into view. It's so big that it's taken light 13.8 billion years to reach us from the edge of it. It's this big round sphere here, which we affectionately know as our universe. But what is that weird ball? Everything else I talked about was kind of intuitive, right? If you go farther away, you see more stuff. But why does it look like we're inside of a strange green and yellow ball? Now, to understand that, it's not enough to talk about our place in space. We also have to talk about our place in time. Unfortunately, we can use this sky as a time machine. We just talked about how it takes, so how long did it take for light to reach us from the sun? Do you remember, guys? Only people under 15 can answer. Yeah?
I'm pretty sure it's like 1 minute.
Pretty close, yeah, it's minutes. 8 minutes, that's right. So, and when we look farther away, we see things that has taken longer for light to get to us from. And here, in this photo from the Hubble Space Telescope, we can see a lot of galaxies that has taken about 13 billion years to reach us from. And what have we learned then about our history from looking at all these different stages of our past? Well, we've learned something very surprising. And to appreciate how surprising it is, I want you guys for a moment to suspend your disbelief and pretend that you're each a galaxy, okay? And I'm looking out at you with my telescope. What do I see? I see that in the front row, everybody is in their 90s with canes and so on. And then here I see a bunch of people in their 60s, then in their 40s, and then a bunch of teenagers, and then at the back there, I see a bunch of toddlers. And in the very back, second back row, they're just infants. The very back row is completely empty, nobody in it. Very strange. And if that wasn't weird enough, the back wall of the Robbins Library room here is glowing at me with a strange glow of microwaves. And to further add to my puzzlement, I noticed that you guys are all blushing. You guys in the front are just a little bit pink in the face, but those of you in the back are like tomato red. So what is it? Was it something I said? You know, what's going on? Yeah, this is exactly what it actually looks like when we observe galaxies with our telescopes. So how can we understand this? Well, first of all, as we just talked about, the farther away you look, right, the longer it's taken light to reach us from there. So if I stand out here, nearby, I'm going to see galaxies the way they were quite recently, when they were quite old. If I look really far away, I see galaxies the way they were in the distant past, when they were very young. So far away, we can only see small galaxies that are not really fully formed yet. And if you look, so that's the second last row, like here, the toddler galaxies. And the very last row of the classroom that was empty, that's here. No galaxies at all. Why? Because that long ago, they hadn't had time to form yet. Does that mean that this black stuff is vacuum? No. I thought so when I was a little kid. But of course, it can't have been, because there must have been the stuff there that later turned into the galaxies, which we now know is mostly hydrogen gas. But hydrogen gas is transparent. So we can see right through it. It doesn't look like there's anything there. Now, what about the blushing? Why do you all look red in the face? Well, if you go out to down to the freeway 2 here and listen to the cars, they'll go ew. Well, maybe not at this time of day, but otherwise ew, ew. We call that the Doppler effect, that the frequency gets lower when the car is going away from you. The cars don't sound ew, right? They go ew. And it's not just sound that gets lower frequency when something is going away. It happens for light as well. So light, when it gets lower frequency, shifts from other colors down towards the color red. We call that red shifting. So if you galaxies are all red, that means you're all moving away from me. And that's what we mean when we say that we've discovered our universe to be expanding. All the galaxies are flying away, and the fact that those of you sitting farther away are more red in the face means that you're flying away faster. In fact, twice as far away, you're going away twice as fast. And if I come and notice that one of the banks here on Mass Ave has been robbed, and I want to figure out how long ago it was, I can look at how fast the car is driving with the robbers and compare that with the speed, and I'll get how long ago the crime happened. I can do the same with these flying away galaxies. Take the ratio of the distance to the speed. And what's interesting is, since the far away ones are going faster, basically everything was here at around the same time, about 13.8 billion years ago, when you do the math carefully and correct for acceleration and deceleration. So about 13.8 billion years ago, something really, really weird happened. We don't know what exactly, but we have a nice word for it. We call it our Big Bang. We'll come back and talk a little bit more about it. And the last thing we have to understand is why on Earth it looked like the far wall of our room was glowing. Well, that's because it's not just that the galaxies are flying apart, but everything is flying apart from everything else. So the gas itself is being diluted. When you dilute the gas, it gets colder. That's how air conditioning works. So if we run time backwards, this gas gets hotter and hotter and hotter. Now, this is something you can only answer if you're under 14. If you take ice and you heat it up, what does this turn into? Yes, you can just shout out.
Water.
Yeah, water. Solids melt into a liquid. And if you heat up a liquid, what does it turn into? Just gas, that's right. Now here's a tricky question. If you heat up a gas, it turns into a plasma. Awesome, that's right. And a plasma is not transparent anymore. It's opaque. So when we look far away behind all the galaxies, we see an opaque plasma screen, is what it looks like to us, hydrogen plasma. But of course, we see the same thing whatever direction we choose to look. So it looks to us, in fact, like beyond all these galaxies, we see a plasma screen that we're photographing from inside. And when we take better pictures of it, it looks like this. These images were taken from NASA's Wilkinson microwave anisotropy probe, which revolutionized cosmology for a cost of 40 cents per taxpayer. And the one question you might have about this super hard measurement to make is, did they somehow screw up? Well, now we got an even better experiment, the Planck Satellite, which released its data just last year. And look what happens when you go from 3 megapixels to 5 megapixels. Beautiful agreement. Wherever there's a spot, there's still a spot. except you can see it's an even sharper image now. So these are photos, baby photos of our universe, the way it looked only 400,000 years after our Big Bang, about 13.8 billion years ago. It's pretty remarkable. However, even though we've figured out a lot of stuff, huge mysteries remain. So let's not get arrogant. For example, from these kind of awesome measurements of galaxies in the microbackground, we've figured out that only 5% of all the stuff in our universe is made of atoms, which I used to think back in school when I was 10, was everything. And we know that there's at least two kinds of stuff we don't understand, dark matter and dark energy. We also don't know exactly what happened 13.8 billion years ago and caused our Big Bang. We also don't know what's going to happen in the distant future, whether there's going to be a big chill where everything keeps expanding forever, or a big crunch where it all comes crashing back on itself, or a big rip, or a big snap, or death bubbles. There are a lot of different cosmocalypse scenarios that you can ask me about. And how do we answer all these questions? Well, the good news is that to answer all of them, what you really need to do is map our universe, this region that we can observe, better. And the good news is we haven't mapped hardly any of it yet. Look how little we've accomplished if we peel off the surface of this. All those galaxies that I flew you around in the very beginning, or just this little region here, okay? Less than 0.1% of the volume. And these baby pictures of our universe, from that plasma screen, which we've taken with these microwave cameras, are just the thin yellow surface here, which is a puny fraction of the volume too. So if we can map all of this stuff, that'll be awesome, and it'll shed great new light on all these questions. How do you do that? You cannot build bigger ordinary telescopes and see galaxies that are over here, because there aren't any galaxies that far away, as we talked about, right? They haven't formed yet, so you read my mind, exactly.
Maybe that slice at constant 13 billion year time or something.
Exactly, but when we see it the way it was when the light left there to go to us, precisely. So what else can we do? Fortunately, there is something else we can do. It turns out that all of this hydrogen gas that's here gives off not visible light, but it gives off radio waves. And they're in fact 21 centimeters long when they're given off, and then they get stretched when they fly through our universe to us. And by measuring how long they are when they get here, we can figure out where they came from. And with this, we can make three-dimensional maps that are 100 times bigger volume than anything we have so far. And we've had a lot of fun at MIT building a new kind of telescope to do exactly this. And to convince you of how easy it is, I want to show you how we can do it, the whole thing in just 2 minutes. easy. It takes only 2 minutes if you move fast. I'm so happy to see so many kids here, and I hope you take away from this that doing science is really, really fun. And one of the most fun things about it is you get to just hang out with such fun people. In fact, we built this up 4 hours drive northwest from here up in Maine to get away from all radio stations, so we could measure these radio waves from the distant universe. So we drove up together, and then we all worked hard to set this up. Then half of the crew went whitewater rafting, while the rest of us took data. And then those who survived that took data the next day. We switched. So doing science is a lot of fun, and I was very happy to hear that all of you kids I talked with said you liked math and science. So keep it up. Maybe I'll see you at MIT. Now, we've talked here about about two themes. I first mentioned that we've discovered again and again that everything we thought existed was just part of something bigger, that reality is larger than we thought. But I also want to emphasize that, and you've seen here, how we humans have been able to figure out much more than we once thought we would. When Native Americans walked these lands, over 1,000 years ago and looked at the stars, or when people elsewhere on the planet looked at the stars long, long ago, they made up beautiful myths for what these shining dots were, right? But the people who really thought hard about it kind of felt a little bit melancholy, I think, knowing in their hearts that they could never really know for sure what those shiny dots were. You couldn't jump up and touch them, you couldn't, and so on. And yet, now, we've been able to not only figure out what the stars are, but we've figured out that we're very connected with them. We've figured out, in fact, that you guys, all the oxygen that's circulating around in your blood was made by stars. So not only are you in the universe, but the universe is in you. And we've discovered even more amazing things about the age of our universe and the origin of it. So how have we humans been able to figure out so much? Partly it's, of course, because the human mind just turned out to be even more awesome in its abilities than our cave-dwelling ancestors once thought. They had no idea that the mind was capable of writing and composing and writing and doing poetry and all sorts of wonderful things. But I think there's more to it than just that. I don't think the fact that we've figured out more is only telling us something about ourselves. I think it's also telling us something about our universe. I think we've been able to figure out so much because we've discovered that our world hides an elegant simplicity and beauty, which is revealed by mathematical patterns and shapes, by clues that we've been able to find, basically. So if you ask me what are the most useful ideas that have ever emerged in science, I would say there are two. The first one is we should do experiments, basically measure stuff. And the second is that when we measure stuff, we should try to make mathematical descriptions of what we measure. And again and again and again, that's turned out to be enormously successful. This was discovered already in ancient Greece, and Pythagoras exclaimed that, numbers rule the universe. And about 400 years ago, Galileo famously exclaimed that nature is a grand book written in mathematics. But what did these guys really mean by this? I mean, I look around myself in the room, where is the math that they're all talking about? Oh, I see. It says 5 there on the clock. But that's kind of cheating, isn't it? Because some human just wrote that there. That's not, we don't see big numbers written in the sky. So where is all this math? Well, in the Galileo quote, if we read it a little bit more carefully, we find the answer. He says here that the book is written in the language of mathematics, and its characters are triangles, circles, and other geometric figures, and so on. So he's using math in a slightly broader sense. So geometry is also math. Patterns and shapes are also math. And patterns and shapes, yes, that is something nature is absolutely full of. Recurrent patterns and shapes. What do we call this shape? Only people under 15 can answer. Okay, 20. Yeah. Yes, awesome. You guys are awesome. This is a parabola, and it obeys a very, very simple equation, y equals x squared, if you label it like this. And everything you ever throw, whether it be a water bottle or a rock moving under gravity, always moves in this same shape, a parabola. If you look up into the sky and you look at the planets, you were doing a project on extrasolar planets, right? They all move in this kind of shape. What do we call this? The one that looks like a squished circle. Ellipse. Yes, exactly, an ellipse. they all move in ellipses, and if you look more carefully at an ellipse, it turns out that a small piece of it is shaped, near the tip is always shaped exactly like a parabola. And if you work out more accurately, like in college, how this actually moves, it's not exactly a parabola, it's actually the tip of an ellipse. So, and that's also described by a simple mathematical equation. So let me ask you a little pop quiz question. That's a bad habit I have as a professor. I love giving pop quizzes. So look at these discoveries. Neptune, the radio wave, and the Higgs boson. What tool was it that triggered the discovery of these things? Yes, mathematics. If you want to be a real stickler, you could say it was the pencil that was the tool. But they were all predicted through mathematics. For example, Neptune, in 1846, Urbain Le Verrier in Paris was wondering why the planet Uranus, which had recently been discovered with a telescope, was not obeying the equations of gravity that Newton had figured out. And he sat there and he calculated and calculated and calculated, and then he wrote a letter to this astronomer Gall in Berlin and said that if you point your telescope to such and such a place in the sky at such and such a time, you will there see a new planet. I imagine when Gall got this letter, he probably figured that this Frenchman was cuckoo for Cocoa Puffs, but he must have been so curious. He pointed the telescope there anyway, and boom, there was the planet Neptune, predicted through math. Then just decades later, James Clerk Maxwell sat and took all the measurements and patterns people had figured out with magnets and electric wires and stuff. This is what I've been teaching my course on at MIT this semester, and we had 900 exams to grade yesterday. And he calculated and calculated and calculated and realized that if you built a certain kind of device, you could use it to send information through empty space that would travel at the speed of light. Later on, this exact device was built, and it worked. And raise your hand if you have a cell phone in your pocket. Yeah, it's predicted through math again. Right? Even more recently, Peter Higgs took the most advanced mathematical description we had of physics, the standard model of particle physics, and calculated and predicted that if you build the most sophisticated machine ever built by humans in Geneva, and you use it to smash particles together near the speed of light in a certain particular way, you will there produce a new kind of particle, the Higgs boson. The machine was built. You know how it went. He got a free trip to visit my hometown of Stockholm. So, all of these things were predicted through mathematics, and that's just a few examples I selected. We can, with the equations here, that in fact my wife has been forgiving enough to let me put up in the living room, you can capture and make an enormous amount of predictions about the physical world. Some people get so into their equations they even put them on their tombstone. So there's a lot of math, clues that have been that nature has revealed to us in the form of these equations. And it's not just shapes and equations, it's also numbers. For example, if you ask how many pencils can you put perpendicular to one another, you get 3. Right? That's a number, the dimensionality of space, which is just sort of built into our universe. There are also a lot of numbers, like the ones here. Turns out there are exactly 32 numbers with decimals on them, from which we can calculate, in principle, every single pure number we've ever measured in the history of physics. If you want to know why is it that a proton is 1,836 times heavier than an electron, well, we can calculate it from these numbers and those equations. It's pretty remarkable. So this really begs the question, why? You know, but by 1960, Eugene Wigner was so intrigued by this, he wrote a famous essay saying that this enormous usefulness of math in the natural sciences is really something bordering on the mysterious, and there is no explanation for it. So in the book, I explore the full range of possibilities here, from that there is no explanation to that maybe math is just approximately describing things, to the most extreme opposite end of the spectrum, namely that there really is an explanation, which is my personal guess. So, and I think that there is an explanation, and that the explanation is that our universe isn't just described by math, but it is math. And more specifically, that it's a mathematical structure, which it basically boils down to saying that I think our world doesn't just have some mathematical properties, but it actually has only mathematical properties. And when you think about that, that sounds totally ridiculous at first. For example, just 2 days ago in our backyard, I saw Mr. Hoggle, the groundhog who lives there. In fact, he might be annoyed if we said that he lives in our backyard, because he probably feels we live in his backyard. And he'll claim that his family moved in first. It's over in Winchester. But if you look at him and you ask, like, what properties does he have? Property of cuteness, herbivousness, fluffiness, that doesn't sound like mathematical properties at all. So what do I mean when I say it's all mathematical? Well, Mr. Hoggle's and everything else in our world, we've discovered through physics, is made of these elementary particles like protons and electrons. And what properties does an electron actually have? It has the property -1, 1/2, and 1. And we physicists have come up with nerdy names for these kind of properties. We call them electric charge and spin and lepton number. But the electron doesn't care what we call these properties. It's just numbers, just mathematical properties. And as far as we can tell, neither the electron nor any of the other particles that make up everything in our world have any properties at all except these numbers, these mathematical properties. In fact, a friend of mine, his young son was quite upset when his dad told him that the electrons don't have a color. He's like, what do you mean? Aren't they like green or blue? Or everything has like a color and a texture. And his dad, who's a physicist too, was trying to explain it. No, actually, big things do, but the electron doesn't. And so that's all the stuff in space, only mathematical properties. What about space itself? I already mentioned that space has this property of 3, which is also a mathematical property. Einstein discovered that space also has some more properties called curvature and topology, but they're also purely mathematical properties that if you guys go on and study advanced math, you'll study in math class. So if you take seriously this idea that actually both the stuff in space and the space itself has only mathematical properties, it starts to sound a little bit less crazy to say that everything has only mathematical properties. And so in summary then, we humans have really repeatedly underestimated both the size of our physical world and the power of our human minds to understand it. What does this mean for us, bringing it back home now to Arlington and to our own lives? Well, first of all, I think this is actually a very optimistic thought, because if I'm wrong about this and there are some properties of our world that cannot be described through math, that means that science and physics will eventually hit a roadblock that's insurmountable, where we just can't go any further, because nature is going to stop giving us any more of these clues that have helped us again and again and again in the past. Whereas if my guess here is correct, and it's all mathematical, then there is no roadblock. And our ability in the future to understand our world better and better is only going to be limited ultimately by our own imagination, which I think is a much nicer and more empowering situation to be in. So for example, consciousness, which is one of the great unsolved mysteries facing science today, if I'm right about this, is also something that maybe you, the youngest members of our audience, can figure out one day. Maybe you can understand it as particles moving in beautifully complex ways, processing information somehow, and figure out what it is about the particular nature of the particles, of the patterns of particles in your head that give you this magical experience of consciousness, of feeling the flavor of chocolate ice cream, of hearing sounds and seeing things, as opposed to this, which arrangement of particles, which presumably isn't experiencing anything. Best way to find out, in any case, is to try. Let's come even closer back to home and ask about what this all means for the future of life. So our universe has been around for 13.8 billion years. What's next for us humans? What lies around the corner? As you know, there's been a lot of speculation about this in books and movies. Some very optimistic. After all, there's nothing in the laws of physics saying that life can't one day spread out into the cosmos, where you have 10 to the power of 57 times more space to do cool things. But there are also a lot more worrisome scenarios people have worried about. We have, thanks to this technology that our understanding of the world has given us, also come up with a lot more ways in which we could conceivably wipe ourselves out. We could accidentally wipe us out in many different ways. So Ray Kurzweil, who lives here not too far away part of the year, thinks that one day we'll develop computers which will be smarter than us, and he thinks that's going to be the best thing ever, and he's going to upload himself and become immortal. Other people think that yes, that will happen, and it's going to be the worst thing ever, and there are a lot more worrisome scenarios than silly movies like that. The short answer is we clearly don't know what's going to happen, and it's ultimately very much up to us. What's interesting, I think, is if you take all the things that you could worry about for the future and you organize them like I did here by how far into the future they're most likely to get us, it's quite striking that all of the most urgent things that could wipe us out the soonest are things we cannot blame on Mother Nature, but only on ourselves, things caused by our own technology. So there's also an optimistic twist to this, because it means if we get our act together and don't wipe ourselves out, then we have much more time to face down the various challenges that our universe throws at us. And if you ask me later in the Q&A, I can tell you what to do about killer asteroids heading towards Earth. I can even tell you a very nice technical solution for what to do when the sun starts getting too hot and boiling off the oceans, and how we can totally solve that problem, as long as we can get through the crunch first. So I confess that I, as a professor, have some bad habits. That I like to give pop quizzes. Another bad habit I have is I like to give grades all left, right, and center. So I decided to give humanity a midterm grade for Risk Management 101. And I thought about it, and I asked some friends, and they thought maybe a, I don't know, B plus. You know, we've done some stupid things, you know, almost wiped ourselves out various times, and but we're still here, so maybe a B plus. But I actually decided to give us a D minus. And that's even though I'm known at MIT as being a really soft grader. So I want to just explain a little bit why. From the standard perspective, before we learned so much about our cosmos, you might say, oh, it's a B plus, you know, because, you know, what if we have, I don't know what the probability is that we're going to wipe out and go extinct in any given decade. It might be really big, like 1 in 10, or it might be really puny, like 1 in 10,000. But if you're only looking on a horizon of 100 years, maybe that's not so bad. But if you think in a cosmic perspective, where we have billions of years at our disposal, right? Playing Russian roulette like this over and over again once per decade is just a really, really lame long-term strategy. And there's just so much more potential that we stand to squander, right? Because you have this incredible cosmos out there. So that's why I decided to give it D minus. And just to give one single example of how short-sighted we humans are and how ridiculously little attention we pay to long-term issues of the survival of our civilization, let me just show you one slide that I think says it all. Which one of these two people is more famous? I'll give you just one little clue, okay? The one of these two people who we should all thank really for being here tonight, because he single-handedly stopped a Soviet nuclear attack during the Cuban Missile Crisis. Not Justin Bieber, sorry. And that's really pretty strange priorities for our species, isn't it? So why is this then? Why is it that we pay so little attention to the things to do with safeguarding the future for our children and grandchildren and so on? The most common response I get is, well, you just don't have the money. I mean, it's expensive and the economy is rough, and you know. But I'm kind of a numbers guy, so let's look at the numbers a little bit. There are actually some organizations that are working hard to try to do something about thinking more long term and deal with some of these risks. Maybe the best funded one of all right now is the Union of Concerned Scientists, and it's based right here in Cambridge. They managed to fundraise about $20 million last year from generous philanthropists. They do great stuff. But 20 million might sound like a lot of money. But let's shrink the 20 million down so it represents this many pixels. And look at some other things we did last year with our money. Cosmetic surgery, 10 billion. Air conditioning for US troops alone, 20 billion. We're not talking about the military budget here, just air conditioning for troops, 20 billion. No, slight difference in size there. Smoking, 100 billion just in the US alone. And I didn't even manage to fit the largest item here. So I have to shrink the whole slide almost tenfold to even get room for it. And is it really the case that we couldn't spend twice as much on that by carving off a tiny little bit of this or that? It's clearly not about the money. So if it's not about the money, what is it then? Well, another answer I often get when I ask why are we not devoting more energy and resources towards safeguarding our future is that it would be really irresponsible to spend money on risks that are not proven. Think about this a little bit, because this is something you actually hear quite a lot on the news, where you hear people say, for instance, it would be irresponsible to spend money on dealing with climate change if it hasn't been proven, right? But if you think about it a little bit more, there's an obvious logical flaw in this argument, which is most easy to see if you just imagine for a moment that you're in a store buying a stroller for the baby of a really good friend, and the salesman comes up and says, hey, I got this really nice, robust stroller here. It's $49.95, and we've been selling it for over 10 years, have never been any reports of any safety problems or anything like that. But we have this other stroller here also, which is on sale. And I know there have been some reports in the press of it sometimes collapsing and crushing the child and stuff, but honestly, nobody's been able to prove that this was really due to any manufacturing flaws or anything, and it's 20% off. So wouldn't it be irresponsible for you to spend 20% more money to mitigate some risks that haven't been proven? So which stroller are you going to buy for your friend's baby? Pretty easy, huh? But if you're willing to spend 20% more money to safeguard the life of one child, then surely we should feel the same way about spending a bit more money to safeguard the life of every child on the planet, and their children and all future generations ever to live on our planet and maybe in our whole cosmos, right? So in summary, we humans have managed to have discovered that we had underestimated not only the vastness of our cosmos, but also very much underestimated the power of our minds to understand our cosmos, and by understanding it, develop technologies that can make life much, much more fulfilling and healthy and interesting, or alternatively really mess things up. So although we humans are small in the cosmos, we have great power to understand and improve the world around us. So let's make a difference. Thank you. Questions? Yes.
I don't really understand your conclusion at all. When I think of thinking of the universe in terms of my fantasy of what physical reality means, which of course could be completely bizarre, I can imagine having a period where we are like children and we are constantly asking why, and we never end up with a final why. But if I imagine it being mathematics, I don't know, we just end up with a ratio somewhere, and that's it. We can't continue to keep asking why if it's just numbers. So what am I getting wrong?
I'm not sure I fully understand the angle of your question, but if you think about the technologies that we enjoy now, right, what they fundamentally represent is a deeper understanding of how nature works. In this case, people were trying to figure out how atoms worked, which seemed completely useless at the time, and they measured some ratios and numbers. But from that understanding came the ability to build these technologies. And there are still a lot of things today in the world that we don't understand well. If we mentioned consciousness as one, there are plenty of others. And if we can get a deeper understanding, find the mathematical equations that we're missing, then that gives us not only deeper insight, but also even more ability to shape our world.
Your conclusion had to do with a halting point. That if we think of the world in terms of physical reality, we will hit an end point where we will not be able to ask why anymore. But if we think of the world in terms of mathematics,
Yes.
we will always be able to ask another why, one more time, go through another cycle. That's your conclusion, right?
Well, I'm saying that there would be no insurmountable barrier. We could imagine that the history of science had stopped after Galileo, that they figured out gravity, right? And let's think about how it felt to be Galileo. They knew then exactly how the planets moved around in the sky, and Galileo could calculate if I threw something that it would go in a parabola and where it would land and stuff. But he had no idea why, for example, a tooth was hard and skin was soft. That seemed to be beyond the pale of science and something that you could never calculate with equations. But then we got the Schrödinger equation of quantum mechanics that magically describes everything to do with atoms, and now we can calculate exactly the softness and stiffness of materials. We can calculate so many other things which seemed like they would never be understandable. We can even, with computers, simulate in advance which kind of materials will have certain properties. That's how a lot of discoveries are made these days. Even a lot of medicines are made this way. People use math to predict, and then we build things. So all I'm saying is, if there are no roadblocks in place, that means that the kids here in the audience, right, can go after any open problem knowing that there's at least a possibility for them answering it. We don't know for sure whether it is this way or not, but I think it's a very good working hypothesis that it is possible, because there's no better way to fail, as you know, in any endeavor than to convince yourself from the get-go that this is impossible, right, and therefore not even try. So let's take a question on the, was there a question on the right side? Yes.
Sorry for my voice.
I can hear you loud and clear.
Should I stand?
Well, you can take this.
Thank you. Hello? Yeah. Well, I'm a mathematics teacher and a physics teacher as well.
Oh,
but
great.
on the high school level. And my problem is not with most of what I hear. But when students come to me, some of them are your fans, I'm sure. But they'll come to me and say, what about the multiverse? Is that really physics?
Mhm.
Okay. As a teacher, you know, they put a certain trust in you. And so I want to know from you, if you were in my position,
Yeah,
what would you tell them?
that's a wonderful question.
I know what I would tell them. I just want to know what you
Yeah, first of all, I would tell them it's a great question, because it is. You know, and at first sight, it sounds like obviously parallel universes has to be just science fiction and beyond the pale of science, because science is about measuring stuff, about testing theories, and how can you, if you can't even go there and see it, surely it's not testable. However, the interesting thing is that the parallel universes that I talk about in the book are not theories, actually. They're predictions of certain theories. So it's very important to understand this logic. For example, we have this theory of gravity that Einstein gave us, general relativity. It's a theory. I showed you the equations of it earlier here. And why is it science? Because you can take this and you can predict a bunch of stuff, and it predicts that the sun should bend starlight in a certain way. It predicts that Mercury's orbit should be a little bit altered in a certain way. It predicts that your GPS signal should be delayed in a certain way. We can test it. Okay, this is the theory. That means we have to take seriously everything it predicts, even things that we can't actually ever test and observe, like what happens inside of black holes. So one of your students could also ask, equally legitimately, hey, teacher, are black holes, is that really science? Because I can't go inside of a black hole and measure stuff and then come back and publish the result in the Boston Globe or a science journal. It's a one-way ticket in there. So is that science? Yes, it is, I say, because this is what's testable. And if we take seriously a theory, we can't just opt out of its prediction and say, I don't like black holes. I'm going to use Einstein's gravity for everything else, but I'm going to opt out of that prediction because I don't like black holes. No. If someone doesn't like black holes, they need to come up with a different theory of gravity that doesn't have black holes, but they can still explain everything that Einstein's theory can. That's why we take the black hole in theory seriously. So there's a beautiful analogy between what I just said here and parallel universes. We have this theory called inflation, which is the best theory we have for what created our Big Bang, invented by Alan Guth over at MIT. And it has made a whole bunch of predictions that we've tested. It's a mathematical theory with equations, and the most spectacular prediction it ever made was just confirmed sensationally just 1 month or so ago by a Harvard-led team, where they found these enormous ripples in space-time called gravitational waves. So that's a theory too. If we take seriously inflation, then we have to take seriously what it predicts. And it actually predicts that space isn't just the universe that we can see, but that space is much bigger than that. So does that mean we know for sure that there is this bigger space that we can't see most of? No, we don't know that for sure, because we don't know for sure that inflation is true. However, is inflation a scientific theory? Yes, absolutely, because it's testable. And that means that we have to take seriously also this idea that we can't see all of space. So I would say to your students, yes, this is a scientific theory, but it's a controversial one, and we don't know yet. And there are measurements going on to test these theories that predict
So
it.
that's what you would say to my students.
That's what I would say to your students.
Now, can I tell you what I would
I would love to hear.
Well, I would tell my students that the science that we inherited from Galileo
Right.
is based on a certain ability to test. And mathematics or not, if it's not accessible to experiment, we don't have to accept everything together. General relativity is a very powerful theory, but some aspects of it even Einstein didn't accept, okay? And we accept the existence of black holes because we have observed them. So it's not just everything that are in the textbooks that I teach to my students. The reason certain things aren't in the textbook is because they aren't accessible to experiment. Now, maybe on a different level when you're teaching graduate students and postdocs and people who are working on their PhDs and stuff like that, they have a liberty and a freedom and a marketing opportunity available to them with those credentials to say certain things that I don't have a right to say. See, I can't stand before my students and tell them that we live in a multiverse.
But I wouldn't say that either, because we don't know that.
Well,
But what I would say, and again, your students, you're free to tell them whatever you want. I think it's wonderful that you teach them critical thinking and don't let people pull wool over their eyes. But the fair statement, which I stand by, is this is a testable theory. And it's true, we have seen observational evidence that makes us think black holes exist, but you will agree with me, we have absolutely no experimental evidence at all for what happens inside of black holes. Because that we have not seen, and we can never see. Right? But we're allowed to talk about it because this theory predicts it, right?
that's speculation.
It's no more speculation than general relativity is, because the only way to get rid of the interior of the black holes is to get rid of this theory, right? And people have tried for 100 years to come up with a better theory of gravity, and they've all failed so far. And because of that, we need to take this pretty seriously. We don't have to. Yeah. I just want to give my perspective on it.
But I just want to mention
Yeah.
something to you, that when you talk about general relativity, it has limitations. Einstein himself was searching for a unification
Right.
of both gravity and electromagnetics.
Yeah.
If he didn't believe it had any cosmological implications, why would he do that?
You're quite right that none of these theories are the final word. So for you kids in the audience, you should know that this beautiful theory of Einstein doesn't get along with this equation here, the Schrödinger equation of quantum mechanics. They don't talk to each other. That's why they're in opposite corners of the screen. So if you can figure out a theory that unifies them, I can promise you a free trip to visit my hometown. Thank you. Thank you so much. Any more questions? Yes.
Are there any ideas about experiments or observations that could connect multiverse theories with data? Anybody have any ideas?
Oh, yeah. So the way to test or kill all of these ideas of multiverses is to test the theories that predict them. So thanks to this excellent question we just got here, the way to test what I call the level 1 multiverse in the book, which is the idea that, so our universe is simply the region of space from which light has reached us so far. And the level 1 multiverse is simply the idea that space is much bigger than that. The way to kill that idea is to rule out the theory of inflation, which predicts it. And that's exactly what this team at Harvard set out to try to do. Because it had predicted that there would be these certain signals in the sky. They looked for them, but instead of ruling it out, they found the prediction. So now people take it even more seriously. But the way it works in science is no theory, no matter how many confirmations it's had, can ever rest on its laurels. We can never prove that things are true. People will keep making better experiments, and maybe they will eventually rule it out. It's the same thing for the quantum parallel universes, the level 3 multiverse. If you try to build that thing follows simply from the assumption that this equation is correct. So if when you try to build a quantum computer, which is something that millions and millions of dollars are being invested in doing right now, a type of device which can solve a problem that would take longer than the age of our universe to do on today's best computers in under a second. Okay. If you try to build such a device and it doesn't work, and you study it and you realize the reason it's not working is because this equation is wrong, then you've not only killed the Schrödinger equation, but you've ruled out the whole level 3 multiverse. So there are a lot of exciting things that are tests are actually being done now because there's money to be made from this, that it's going to be really fun to see how they turn out. And until then, we should keep an open mind on about these matters. Yes?
Can you explain what multiverse is and how it applies to inflation?
Sure.
Yeah.
So, first of all, when we talk about our universe, again, we simply don't mean everything that exists necessarily. We simply mean this spherical region of space that we have access to, that light has had time to reach us from so far since our Big Bang. And if you take a step back and you say, okay, let's just consider everything that exists, all of physical reality that exists independently of us humans. Then, after a while, we humans evolve on our planet, we come on the scene. We can ask, okay, how much of this full reality are we actually able to observe? Either all of it or not all of it, right? If we cannot observe all of it, then by definition there are parallel universes. There are other regions of space which we have no access to. Okay? Which way is it? We don't know. But I think it would be quite arrogant to have and just take for granted that there's some sort of fundamental principle that says that we can observe everything. That to me sounds dangerously close to an ostrich standing there, with its head in its hand saying, if I can't see it, it can't exist. And particularly since we humans have just made this mistake again and again in the past, taking for granted that all that existed was even less than we already know to exist. I think we should be very careful and not get arrogant and be a little bit humble. So parallel universes simply are regions of space as big as our universe out there that we have no access to. And as I talked about in the book, there are actually several different kinds of them. And it's interesting to do the kind of experiments we measure to try to see whether we should take this seriously or not. And
how does inflation, the theory of inflation, account for the multiverse?
Oh, good. So inflation, the theory of inflation is basically a universe creation mechanism that Alan Guth discovered. It's a mechanism that produces big bangs. Start with almost nothing and makes vast space that ultimately gets galaxies and stars and planets in it. Now, why would you expect something like that to give you a multiverse? Well, suppose you have some mechanism, some kind of machine that produces paper clips. Or let's take cars, it's more fun. You have a car factory. A car factory usually doesn't just produce one car and then stop. It usually produces many cars. If you have a rabbit producing mechanism, like mommy and daddy rabbit, they usually produce, again, more than one rabbit. So if there is some kind of physical universe production mechanism, it's not so crazy to think that maybe it produced a whole bunch of universes, of Big Bangs. And that's exactly what inflation actually predicts when you do the math. That our Big Bang is simply one out of many.
Okay, thank you.
Yeah?
Yeah, I'm just partway through your book with these fascinating concepts of the levels or tiers of multiverse, a little puzzling, but we don't have time to get into all that right now. But if I could just ask a general question about it, is it, and maybe this will spoil the end for me, I don't know. Is it stated or implied that if there are multiverses, and I think we're in agreement we can't answer that question yet,
Right.
that whatever they are in any of these tiers, that they either would or would not exist in the same three space that we exist in, or would they maybe share one dimension with us, but other dimensions would be.
Excellent question. So you're asking if they exist, where are they? And are they in our three-dimensional space or not? The answer is that the first two levels, level 1 and level 2 multiverses, if they exist, are actually in our own three-dimensional space. So instead of using such a fancy, schmancy sounding word as level 2 multiverse, you could just say space. So you have a space that's really, really vast, maybe infinite, and we can only see a small, small part of it. And the difference between the level 1 and level 2 is not just how far away you are, but it's how diverse things are. So if you go really, really far away, but still in the level 1 multiverse, you would still learn the same things in physics class if you were over there. But you might learn you would learn different things in history class, because over there all the atoms started out in different places and the solar systems formed differently and different things happened. But if you go even farther away in space, if the level 2 multiverse exists, you would even learn different things in physics class. You might learn in school that actually, the periodic table has only 17 atoms in it, for example. So there's more diversity there. So that's the answer to that question. Yes?
So by implication, are you basically subscribing to the anthropic principle that we're only here and observing it because our universe happens to have the conditions, the starting point that allows us to exist?
Yes, with a caveat that I don't like the name principle, because the word principle makes it sound like it's somehow optional, even though it's really just the use of correct logic, which is not optional, right? Even if we look at the part of space that we can see, with all these galaxies and stars we flew around in, are we living in a typical part of space? Absolutely not. If we were to just go, let's snap our fingers, like with the infinite improbability drive in Douglas Adams' trilogy, and go to a random point in our space, we would look up and we wouldn't see anything. We wouldn't even see any stars. We would be in an intergalactic void somewhere where it's too dark to see anything at all. Are we surprised that we're not having this lecture tonight there? No, of course not. If you ask what fraction of all space is actually in a solar system, or let alone within 1,000 meters of a planetary surface, it's a puny fraction. But are we surprised by that? No, not at all. Of course, life will exist in those oases, in those bio-friendly regions where it can exist. Even in our own solar system. I mean, raise your hand if you're surprised that this lecture is not taking place on Venus, where it's 900 Fahrenheit right now. Or on Mars, where there's no oxygen. I didn't see any hands, right? You could call that the anthropic principle too, but I think that's making it sound more highfalutin than it really is. We shouldn't expect to find ourselves in a typical point in space. We should expect to find ourselves in a typical place where there is life that asks this kind of questions. And for some reason, some people have gotten more worked up about it when you start using the exact same logic just to regions that you can't see. But I don't think there's anything particularly different really about it. And yes.
Yeah.
Did you have a question? Yeah?
Go ahead.
You have to police us also, because you're the one who knows how long we're allowed to be here. Yeah?
Well, you asked a minute ago if everything that exists we can see. But if it did, wouldn't that put us in the geometric center of everything? Isn't that about as arrogant as you can get?
Oh, I think I completely agree. Be about as arrogant as you get. If you really want to be an ostrich and say, I believe, I have this principle that everything that exists is something I can see, then that's what we can see is a sphere of space, right? The sphere from which light has had time to reach us so far. That must mean that for some weird reason, our planet that we happen to evolve on, isn't a random point. It's not even a random planet. It happens to be exactly at the center. It's like trying to put ourselves in exactly the center of things is really, really awkward. And to make it even worse, if everything that exists is what we can see, well, then we can wait 1 more hour. And then, oops, now light has reached us from a little bit farther away. So that already shows that the idea was wrong. If everything that exists is what we can see only right now, it's not going to be true anymore in 1 minute. So I don't have a single colleague, actually, who would say that. So reality is probably bigger than what we can see. The question is sort of how much bigger. I also just want to add a little emotional point here, because some people seem to get really depressed by the idea that space is bigger than we thought. I think it's the other way around. Now, what is it? Is this people have like some kind of inferiority complex? We need to feel really big? I mean, first of all, yes, we are very small compared to stars and galaxies. But so what? I mean, your brains are the most complicated, the most beautifully intricate and complex patterns that we have ever discovered in our entire universe. That's nothing to feel inferior about, right? And moreover, if we are the only planet in this part of space that we can see with telescopes, then why are all these galaxies so beautiful that we looked at? It's because you are looking at them, right? If there were nobody looking, they wouldn't be beautiful. They would just be a giant waste of space, as far as I'm concerned. So it's not that our universe is giving meaning to us, but you are giving meaning to our universe. You shouldn't feel insignificant about that. You should feel very significant. And what about the size? I mean, suppose you get shipwrecked at night, and then the next morning when the sun rises, what would you prefer to discover? That you're stuck on this puny island that's 50 yards across, or that you're on a continent? If you find yourself in something bigger with more opportunities, surely that's better. Well, that's exactly what we humans have discovered, right? And finally, in terms of this business about feeling significant, we talked about how we are kind of at a fork in the road now, humanity, where we can, maybe in our lifetime, it'll get decided whether we're going to wipe ourselves out or get our act together and let life really flourish, right? And if in the distant future, our whole universe is teeming with life, I don't know what these distant ancestors of ours are going to think about us, but they're certainly not going to think of us as insignificant, because it's what we did on our little planet in our lifetime that made all the difference.
I have to stop here because we're all over here. So thank you very much.
Thank you. Thank you so much. And you kids, keep studying science in school, and I hope to see you all at MIT, all right?